Alright, today we're going to start our new unit on circuits. We've all had some experience with this before. So the first thing that we're really going to talk about with circuits is the battery. This is how we draw a battery in a circuit. It looks weird, but it's the same thing as, the battery that we're used to. This is the positive end and this is the negative end. With this drawing of the battery, this is the positive end and this is the negative end. And what a battery does for us is supplies constant potential difference. Voltage is really what we're talking about with that. So on a battery like this, the voltage is 1.5 volts. What that means is that the bottom of the battery is at 0 volts and the top of the battery is at 1.5 volts. The reason we call it potential difference is because we're interested in the difference in potential from the top and the bottom. Works the same way with this. This side of the battery is 1.5 volts and this side of the battery would be charged to 0 volts. So that's what a battery does. A battery supplies a constant potential difference. So just a little note on these circuit diagrams. All we're going to look at are resistors and batteries in this class. So this would be a circuit diagram. These things are pretty easy. So this thing right here is a battery. This is a resistor, the squiggly thing. And for a resistor, and for a lot of what we're going to look in class, think of something like a light bulb. It's anything that requires electricity to really work, or anything that uses energy to work. A simple look. And these straight lines are wires. And that's a circuit diagram. They're really, really easy to look at. Another note on batteries. Sometimes a battery looks like that in a circuit, and sometimes it's a little bit more complicated, and the battery looks like we've got two of them stacked together. If that's the case, this is still a battery, this is still the positive end, and this is still the negative end. Now, we're going to look at what current is in a minute, but while we have this simple diagram here, we're going to give a rule for current. The term current, whatever that may be, we're going to say current flows from positive to negative. Okay? Current flows from the positive end of the battery to the negative end of the battery. That's just a rule for current. Now we're going to look at what current actually is. So let's pretend that we have a chunk of something. We'll say metal. And inside of that piece of metal, we have a bunch of molecules. These black dots, there's a bunch of them. All of these black dots are going to be the atom, the nucleus of the atom. That's where positive charge lives. And then around those black dots, we'll make them fun. For each black dot, we've got an extra little electron floating around. And that's these green dots. These green dots are electrons. Okay, so that is an electron. So this is a piece of metal. What we're going to do is take and hook up a 6-volt battery to that piece of metal. And we're going to look at what happens when we hook up that 6-volt battery. Now, as soon as we attach this wire to this end of my piece of metal, what we see is that piece of metal now has a voltage of 6 volts on that end and a voltage of 0 volts on this end. Well, as we know from the last unit we studied, when we do that, we're going to get an electric field in this piece of metal, and that electric field is going to point from the positive voltage to that 0 voltage. So we have an electric field here in purple pointing to the right. Now, these electrons inside of this electric field, each electron is going to experience a force. And the force of that electron is going to be in the opposite direction of the electric field. So every single electron is going to experience a force this way. The electrons are going to want to move in this backwards direction. Now, each electron is going to bump into stuff, and so they're going to kind of move like a Plinko chip all the way through. So what happens when we attach a battery to a piece of metal is that we see electrons move, but instead of accelerating, they move at a constant velocity. We call this a drift velocity. We won't have to calculate it or anything like that, but they move very slowly through the wire. And not just one electron, but all of the electrons tend to move at this slow, constant velocity all the way through this piece of metal. And so what we have is charge moving. We have charges move because of the battery. Now, we see here that all of the electrons move in this direction. So, for the battery, electrons are pumped from this end, and again, this is electrons, all the way through until they get to the positive end of the battery. Electrons want to go from negative to positive. These charges are moving because of the battery. And that's what current is. Current we use an I for current, is the movement of charge. And so very basic formula for that is charge over time. My change in charge over my change in time. And my units for that are amps. 1 ampere, is equal to 1 coulomb per 1 second. Charge and time. That's what current is. But if you remember what we said earlier, it's that current flows from positive to negative. This is opposite of what really happens. It's opposite of what electrons do. Electrons, which are the things that actually move, flow from negative to positive. And all my positive particles, which are in the nucleus, stay still. This is something we just have to deal with. It's conventional current. And it's a convention that we're just stuck with. Benjamin Franklin, back in the day, made a guess on what was moving and what wasn't, and he turned out to be wrong, but we're stuck with conventional current going from positive to negative. So current here is going to point from positive to negative. The current's going to move that way, and that way. It's something that we're going to have to remember. Now, the current is still proportional to how much charge moves. So the next thing we're going to look at is what affects how those electrons move through an object. And we refer to that as resistance. Resistance refers to how easy an electron can move through a piece of material. If I have a high resistance, it's not very easy. If I have a low resistance, it is very easy. So let's look at a piece of wire and compare it to a longer piece of wire. And we're going to draw in the nucleuses of all the atoms in here. It's the same spread, but this long one has more stuff in the way. Now, multiple electrons move at once, but let's just say we're one electron and one electron. Which one of these wires is it going to be easier for the electron to move through? Now, this one's short and this one's long. This electron will have to bounce through this stuff. This electron will have to bounce through Plinko style all this stuff. So it is harder to move through a longer wire. It's harder to push charges through that longer wire, which means it's going to have a bigger resistance. And then we're going to look at something that has a much larger area. Now, let's say this has this area much bigger around than this wire. Let's say I'm trying to push a whole lot of charge through each one of these. Guess what? I can push more charge when I have a larger area. Which means the resistance here for this larger area is going to be less than this resistance. I can move more charge through here. So it's easier to move more charge through a longer a wire with more area than it is a wire with less area. So that brings us to the idea of resistivity. Resistivity is a measure of how much stuff is in the way. How much stuff is in the way of moving charges? The higher my resistivity, like in glass, that's 10 to the 14th, the more stuff is in the way. The harder it is to move charges through a given meter of my stuff. The lower, the smaller the resistivity is, like in gold, the easier it is to move stuff through. So a nice little formula we have for finding the resistance of an object is this resistivity thing. We use a rho times the length of my object divided by the area of my object. And this tells me what we just looked at up there. The longer the object is, the higher the resistance. The bigger the area, the lower resistance is. We'll talk about this a little bit more tomorrow.